This is Physics 2212, Lab 2, Lines of Charge. So a little introduction. In Lab 1, we created two pieces of charge tape and observed their interactions with other objects and themselves. And in this lab, we are calculating the charge of each tape by treating them as uniformly distributed charges and simulating that interaction using VPython. So a little results preview. We see that both pieces of tape are positively charged from lab 1, and that in this lab we determined that charge of each tape is 2.63 times 10 to the negative 8 coulombs, and that means they're both deficient in 1.65 times 10 to the 11th electrons. So some important key concepts to know. Gravitational force, Fg equals negative mg, mass times acceleration due to gravity, always going to be the negative y direction. Newton's second law, acceleration is equal to the net force over the mass of that object. And so when the acceleration is 0, the net force is going to be 0. Our electric field of a rod with uniformly distributed charge is found by this equation here. And this is important because unlike a point charge, it considers the length of the tape as well. And our electric force, Coulomb's law, used to calculate the force to an external electric field. So we have the electric field vector that's acting on some charge Q, and we just multiply them together. So some important assumptions we made here. We assume air resistance is negligible. We assume that the charge is uniformly distributed and that both strips of tape are equal in their charge, and basically that they're both identical. So our procedure from lab 1 hasn't changed. So we have our U tape we made from the base tape, observed the interactions between charged objects, and then we also suspended one with the other and measured the distance between the two. So observations we made in lab 1, we found that the U-tapes are positively charged and that they both repelled each other at a distance of 0.027 meters. And for our calculations in this lab, we know that the tape length is 0.2 meters and the tape mass is 0.002 kilograms. So our environment, we have our system that we're looking at, which includes just the suspended U-tape, and then our surroundings that are acting on this system are our held U-tape and the Earth. So we can see here that the electric force on the suspended tape and the gravitational force cancel out, right? And the acceleration is 0. So we know the system is static and that the net force on it is 0, which is really important to know. And so we also have our held U-tape, so our force that we're using to hold it up, and then electric force due to this line charge on this one, and the gravitational force on the held tape. So we can estimate the charge on one of the tapes using the magnitude of the gravitational force and electric force, setting them equal to each other with this fancy equation here. We look for Q, and it's going to be plus or minus the square root of all this jazz. And we know from this experiment that Q is positive, so we kind of ignore this. And we found that Q is approximately 2.47 times 10 to the negative 8 coulombs. So in our computational model, which is a little different from our experimental because it assumes perfect experimental technique, we have our constants, our mass, and then the computational model determined that the actual charge was approximately 2.63 times 10 to the negative 8 coulombs, so a little different. And then right here we have our function that finds the E field due to a certain charge at another point, which is going to be important for integrating. As we see here, we split up the held tape into little DQs and find the DEs for every single little point and integrate that to find the total force from the held tape onto the suspended tape. You see our visualization here. The magnitudes are the same, and the electric force arrow here, gravitational force on this line of blue charges. We have our little green electric field arrows, and then the held tape line charge. So results discussion. The charge on each tape is 2.63 times 10 to the negative 8 coulombs, which we found using estimation and then a guess and check on the computational model. And so our deficient electrons are here, and we use this guess and check by setting the gravitational equal to the electric force and kind of found when they were the same in magnitude using the model. So important sources of error, we got inaccurate measurements of dimensions, separation distance, anything that could possibly happen. The pieces of tape could have different magnitudes of charge due to improper technique, as we discussed, which the model does not incorporate, and also just rounding errors. So discussion, if we modeled each tape as a point charge, we saw in lab 1 that it was approximately 1.62 times 10 to the negative 8 coulombs, but treating them as line charges, 2.63 times 10 to the negative 8 coulombs, which is quite different. And we know that the line charge model has a greater charge than the point charge model. So why do they differ? Well, viewing the charges evenly distributed across the tape changes the actual charge of the tape quite significantly. And the line charge is closer to the real value because it considers the length of the tape, and the tape is more rod-like in structure than like a single point charge. So we would say that the line charge is a much more accurate depiction of the charge of the tape.